Well, hello and welcome everybody. So before we get started, did anybody have any questions or concerns? No, everybody's doing all right? That's good. So let's see, most of you are here. We might as well get started, at least talking about the announcements. So today we're moving on to sections 2.1 and 2.2. So we're really starting to kind of get to the actual calculus material now. The stuff before this was kind of, trying to get you up to speed with the tools you need for calculus, at least the very minimum. There probably will be things here and there you might have to go and review still. But today's a little bit of a lighter day in terms of due dates. You only have this one assignment, section 1.5, due tonight. Another thing is that the class recordings, at least for the last 3 days, are now posted on their daily checklists. So if you missed one or you're interested in looking at one, you can go back and watch it. And then, as usual, there will be a help session tonight from 7 to 8. And that's always, at least for me, they will be on the class link. For you, Yao, it will be a separate link. Okay. So questions about this stuff? Oh, and there was one more announcement that I just reminded myself of. I believe today is the last day to fully drop the course without a W on your transcript. You can still drop it up till next Tuesday, I believe, but you get reduced tuition back and you end up with a W on your transcript, I think. Okay, so, a lot of you, I don't think that applies to, but I just want you to be aware that if you, because the summer classes are pretty intense, and if you're not really up for it, it might be better if you take it in the regular semester, and so I just want you to be aware of that so that you have the option. All right. So if there's no questions, we'll jump right in. So I'm going to turn my video off. So like I said, we're really starting to get into the calculus sort of part of the course. And to me, what calculus is it's the study of functions, of real valued functions, functions that take in real numbers and spit out real numbers. And today we're going to be focusing on, how to analyze at least one or two properties of these functions. So today what we're trying to get at is to answer this sort of question. So how do functions change? So how do their outputs change when their inputs change? Okay, so that might seem a little vague right now, but we're going to look at two aspects of it that are going to turn out to be related. One's easier than the other. The first one we're going to look at is like how functions change over an interval. That's sort of the easier one. So if I have an interval from some number a to some number b, this sort of change will be called, we'll call that the average rate of change. And we'll abbreviate that AROC sometimes. And then there will be this other type of change, which is more what calculus is about, is how the function changes at a point, okay, at a single input value. Okay. Okay, so let's tackle the first one. Let's tackle this change over the interval part. Okay. So it turns out that what we're really saying about change we're interested in like how quickly is the output increasing or decreasing if I change the input a little bit. So the definition we use to describe that is here. So if I take a function f and an interval from some number a to some other number b, this is going to be always defined for us by this equation. So the average rate of change over a to b, it depends on the interval, will always be this sort of, this formula. And the way you can think of this is the numerator is the change in output, and the bottom is the change in input, right? So it's saying, so basically what the average rate of change tells you is if you were to change the input by 1 unit, how much would the output change on average over that interval, right? Okay, and if you, so in this class, we're gonna a lot of times emphasize doing things multiple ways. And the two things I'm gonna emphasize most are we should be able to do things, formulaically, which would be this way, using this equation. But we also want to be able to think of things graphically, like on a graph. So what does this look like on a graph? So on a graph, I'm just going to draw some random function. Maybe you have some function like this. And I choose some interval, say a to, what place will look nice? Maybe b here. Let's choose b maybe here. So the average rate of change, so you have these 2 points on the graph over your endpoints of your interval. And it turns out what the average rate of change describes is the slope of a special line. And you get that line by connecting the two endpoints with a straight line. Okay. So this green line is called a secant line. And if you think about it, there's sort of a triangle going on here. So let's see, what color haven't we used? I probably need the ruler again. So if I draw a triangle here, there's this triangle. Now, what's the height of the vertical part? Well, whenever you're looking at like distance on a graph or on a number line, it's always the bigger thing minus the smaller thing. So if you think about it, this height here is just f of a, right? Because it's the y value. And this one down here is f of b, because it corresponds to this point on the right-hand side. And so this height of this blue side is f of b, or I guess it's the other way. So this height is f of a minus f of b. And the horizontal distance is b minus a. So you'll notice that these quantities are very close to what we had before, right? This is very close to this numerator, right? You'll notice it's the order that they're in, the a and the b is switched here. And that's because if you look at this graph, is this graph going up or down? Is it decreasing or increasing? What do you guys think? The green line. Is the green line increasing or decreasing?
Decreasing.
It's decreasing, right? And because of that, we want the rate of change to be negative to indicate it's decreasing. So that's why we use this other formula. This formula that we used up here would give us a negative number, but it's the same. It's just the negative of this number. Okay. Okay. So let me summarize what was going on here. So the first thing is that a secant line. Just make sure we all know what that. A secant line is a straight line that connects 2 points on a graph. Okay, so it can be any 2 points on a graph. I just happen to choose these two. But anything that connects 2 points where the points lie on the graph of a function is called a secant line. And what we were saying here is the average rate of change of a function f over an interval a to b, the way to think of that graphically is that it's the average rate is equal to the slope of the secant line. And which secant line? Well, you have to choose the one where you choose the endpoints over the endpoints of your interval, right? So you choose a f of a and your other endpoint of your interval. And if you compute the slope here, right, the slope will always be, you'll always get this formula up here, okay? So that's kind of the main point here, is if you want to think of the average rate of change as a formula, you use it up here. If you want to use it on a graph, you kind of think of it as the slope of this line that you draw connecting the 2 points. Okay. Okay. So that's kind of what happens to the function on average. Now we had this other idea about how does a function change at a point, and that's more complicated. Well, maybe before we do that, let's do an example of average rate of change. Okay, so the setup here we have is we have a car that you can imagine is just traveling like along a straight road, but we know that its position, how far it's gone from a certain reference point, is given by this equation here, this position. And you'll notice that we quite often use s for position. And our units are, distance is in miles and time is in minutes. And then the question we would like to answer is, what's the average rate of change And in this context, when you're talking about position, the average rate of change turns out to be average velocity. And we're going to ask what its average velocity is over the interval, say 0 to 3. Okay. So we could do this two ways, just like we said before, So the answer is that the average rate of change is just given by s at the endpoint 3 minus the position at the beginning divided by how long elapsed. Okay, but we have to now plug these into our function, right? So if I plug 3 into s, I would get that thing. If I plug 0 in for t, we get 0 minus 3 squared plus 8 all over just 3. And if we work out what that is, so let's see, that'd be 8 minus, and then this is 9 plus 8. That's what, 17 over 3. And so we'll get some number. What do we get? We get minus 9 thirds, or minus 3, right? Okay, and then what units would that have? Well, if you think about the way average rate of change is defined, the top of it is just a difference of position, so it still has units of position, so that will be in miles. And the bottom will have units of time, so you end up with miles per minute. Okay. And if you were to think of this now graphically, well, we first have to figure out what our original function looked like. It was t minus 3 squared plus 8, so it's been shifted to the right by 3 and up 8. And it's an upward-facing parabola. So it does something like that. Okay, and then the 2 points we would be interested are we would be at time 0, which would be here, and then at time 3, which would be here. We would draw the secant line. And then we would compute the slope of this. And we would end up with minus 3 as well. Right? So that slope of that line is minus 3. Okay, so questions about this so far? Okay, so yeah, now we want to talk about how does a function change at a point? And that's a more difficult question. Because that's like asking, because it's easy to calculate something's average velocity, right? You just have to know how far it went during how much time. But if you want to know exactly how fast something is going at a single moment in time, and you think about like how could you actually measure that, it's difficult, because the only way we really have to measure like speed is you have to take a measurement of how far something went in a certain amount of time, right? But if there's no difference in times, how do you measure it? And the answer is, well, you kind of get around that by, uh, well, there's kind of a little bit of a trickery involved. And so what you do is, maybe it's best if I just show you an animation here. What did I do with it? Okay, so here's a situation. So imagine that the green line is the position function. So this one's an upside down parabola instead of a right side up one like we had before. And we're interested in knowing how quickly is the function changing at the single moment where time is 5, right? So this point here that I'm kind of moving around, 5 comma 2. And really the only way we have in reality most of the time to measure how fast something is going is we have to take, distance measurements at different times. So maybe the first time we do it, we measure its average speed between time 3 and time 5. And we end up with this blue line. This blue line is that secant line. Sorry, there's a lawnmower here. But then you can ask yourself, how could I make this measurement more accurate? And the conclusion you would probably come to if you thought about it for a little bit is the way to make it more accurate is to make it over a shorter time interval, right? Because if I take a measurement over a shorter time interval, the object has less time to change speed, right? It'll be closer to its actual speed. So I might move the endpoints of my interval closer to my 5. And as I do that, as I move it closer and closer to 5, you'll see that it's approaching this red line. They kind of matches up with this red line, right? So all these secant lines, I'm taking all these different secant lines and I'm taking one endpoint and I'm pulling it in to the point I'm interested in, 5. And as I do that, the secant line starts matching up with the special other line. And the special other line is called the tangent line. And that's the slope of the line that's going to tell us the instantaneous rate of change. Okay. So if we go back over here, what we're gonna learn in a little bit. We're not gonna get there today, but this is going to be given by approximating the average rate of change over short intervals. Like right now, that's really the best we can do. And making an educated guess. Later, we'll have a way to do this exactly, called the derivative. Okay. And sort of the way that would work is, let's do an example like that. So let's consider this simple parabola. And then we want to answer the question, what is the what we would call the instantaneous rate of change, or the change at the point of f at the particular number. Which one did I do? 1. At x equals 1. And it works exactly like in that animation we chose. We might first start by saying we're going to calculate the average rate of change over the interval. So we want to choose some interval that contains the number 1. And we want it to be relatively small. So I might start with something like 1/2 to 1 or something. And so what you would do is you would plug in f of 1 minus f of 1/2 over 1 minus 1/2. You would throw that all into the formula, and I'll just tell you that what you end up with is about 4.5. Okay, so maybe you want to make this more accurate, because this is still an average rate of change. It was still over like, half a minute or half an hour or half a second, whatever units you're using. So maybe you repeat this, and now you make your interval shorter. So maybe now you go, just kind of making up numbers, from 7/8 to 1. That's a lot closer, a lot shorter. And so then you would use the same formula. And you would end up with something like 5.625. And you can kind of continue this trend. I'll just do one more. If you want to make it really accurate, you could use a very, very short interval like this, from 0.999 to 1. Plug it all in. And what do you end up with? You end up with, okay. So if you kind of do this process and you look at what's happening to these three numbers, right? We got 4.5, 5.625, and then we got 5.997, right? What number does that look like they're getting close to?
6.
6, yeah. So we might, at least now it's somewhat of a guess, but we might guess that these are headed toward the number 6. And so we might like to say that the instantaneous rate of change, there's a U in there somewhere, of change at x equals 1 is about 6. Turns out it is exactly 6. And we'll figure out how to do it exactly later. But this is sort of just the process. Like if you want to figure out what the instantaneous rate of change at a point is you have to kind of approximate it using smaller and smaller intervals and see what are those approaching, right? And the shorter the interval, the closer to the actual real answer it should be, okay? And this process will be called the derivative. And that's kind of what we're trying to get to here, okay? But before we can do that, this weird procedure we just did where we had to take these numbers and make them closer and closer to something, this is going to be encapsulated in the idea of a limit, okay? Because really, if you think about what we did, we had these intervals where we had like 1 over here, and then we had 1 minus like a little bit, where h is maybe like a small number. And we were computing the average rate of change, right? And we were plugging these in for different values of h, right? For smaller and smaller h's. But if you kind of think about what's happening here, like if you look at these denominators, right? They were getting smaller and smaller. They were getting closer and closer to 0. over h. So we were interested in what happened when h got really, really small. But this thing I just wrote down doesn't make sense when h is actually equal to 0, right? Which is what we really want to know, is what happens when it gets like infinitely small or 0. And because it doesn't actually make sense, we have to somehow get around that using the idea of a limit. Okay, so that's where section 2.2 comes in. Do you guys have questions about this first stuff? Okay, so hopefully you watched at least a couple of the videos, but let me give you a crash course in limits real quick. So let's just look at like one simple example. So if I have the function x squared minus 4 over x minus 2. Well, what is f of 2 here? Can anybody tell me?
0 over 0.
Yeah, and what is that equal to?
And that's undefined, right?
Yeah, it's undefined. So this function does not have an output when f is 2, right? But if we were to go ahead and graph this, we could actually just go back to GeoGebra and graph this. Let's see, can I make a new one real quick? Sure, don't save. And then we divide it by x minus 2. Okay. So what you would see is that it looks exactly like a nice function, just a line, right? So, and if I zoom in on 2, the calculator doesn't actually even see an issue with it. So what's going on here? Well, let me try to explain. Let's go back to here. You know, a proper sketch of this would look like this. And then you'd have some line. That's what it's supposed to be, x plus 2. So you would have some line here. But if you look at the point x equals 2, turns out that we don't have an output there. So there should be an open circle there. Right, so that point should be, I guess we can fix it. Like that. So that point is actually missing from the graph. Okay. But if we think about it, like if I approach 2 from the left or from the right, what these outputs are approaching some number, right? There should be some number here that corresponds to this, right? Okay. And that's going to be exactly, we can figure that out using the idea of a limit. So the idea is if you have a function where a particular value is not defined, but the function makes sense everywhere near it, so like close to 2 but not actually equal to 2, there's somehow enough information in the function nearby to tell you what that value should be. Okay, and the way we would do that here is we would recognize that if we factor the top, we could rewrite it like this. And so if x is not 2, because having 2 gives us division by 0, for all the numbers x not equals 2, I can cancel these, right? And I'm just left with x plus 2, which is this line, right? And so what the limit does is it says, so here's this, the kind of the symbols we're going to use to denote this, is that if I take the limit as x approaches 2 of this function, it's going to fill it in with what it should be, even though it's not actually defined there. So it should be whatever x plus 2 is at 2. So it should be 2 plus 2, which is 4. So if you go in this picture, right, the way our function was written, it wasn't actually defined, but we can still figure out using, algebra that if this function was, if we wanted to make it perfect, we would fill it in with the number 4. Okay, and that's what a limit does, is it says, what should the value of the function there be in like a perfect world? Okay, that's the idea of a limit. Okay. But it turns out there's kind of different kinds of limits. So there's one-sided limits, there's two-sided limits, and there's sort of infinite limits. Let's look at an example of a one-sided limit to give you an idea. And if you want all the technical definitions, you can look either at the videos or at the book. But let's look at an example. So here's an example about one-sided limits. So we're going to consider a piecewise function. This is going to be 2x if x is negative or 0, and it's going to be minus x plus 2 if x is positive. Okay, and we're gonna, we're gonna basically try to answer the question, what is the proper value at 0? So we're kind of asking, like, what's the limit at 0? What should the function be at 0? But when we graph this, we'll see there's kind of a problem in answering that question. Okay, so we basically have two lines here. So for negative numbers, it's 2x. So 2x might look like this. Something like this. And for positive x's, it's a downward sloping line that's been moved up by 2. So something like this. Okay. And so let's see, the less than or equals was with the negative side, so that part's filled in. And this has an empty circle. Okay, so this would be the graph of our f of x. Is everybody okay with that? Any questions about that? Well, here we might think that there's kind of two natural values for what f of 0 should be, right? We might think it's the top one, we might think it's the bottom one, or because there's two, maybe we think we should take like the average of them or something. And all of those things are fair things to do. But to sort of encapsulate this idea, there's this idea of a one-sided limit. So a one-sided limit, so I'll just tell you about like left limits. A left limit So here that would be the limit as x approaches 0 from the left. So from the left means you put a little minus by it. That tells you that it's from the left. You put it as a superscript and what this tells you is what the value of the function, even if it's not defined, it doesn't matter whether it's defined or not, it can be defined or not defined. Function should be in some sense if we only consider the left half. To the left of 0. So you can do this at any point. I'm just doing this, like you could do this at 1 or 2, but we're doing this at 0. So what it's saying is, if I deleted the right half, if I deleted the right half, then there is only one natural candidate. And the idea is, we call it the left limit because it's, it's either from the left, or people like to say, as I approach from the left, my outputs are approaching this number. Okay, and that would give you the left limit. And so that number looks like it should be 0 to me, right? Okay, so let's put these other things back in, the other half. Okay, so what we would say is we would say that the limit as x approaches 0 from the left will be 0. But now if I try to do the limit as x approaches 0 from the right, if I'm coming from the right, then I forget everything to the left. So I would imagine that this part was just wasn't there. And I would say if I come on from the right, what are these outputs approaching? And they're approaching this number here, right, that I'm putting in green. Even though the function doesn't actually have a value there, we're still looking at what it's approaching. And how would we figure that number out? Well, the right-hand side of this equation came from this equation, right? And so that equation at 0 would be negative 0 plus 2, which would be 2. So in this picture, this number is 2. Okay. So that's basically how you think about left and right limits, is if you only come from the left, only care about the left part of the graph, what does the function look like it should be? If you come in from the right, what does it look like it should be? Okay, those are left and right limits. Okay, let's see how much time we got. I want to give you some time to work on a couple problems. Then there's two-sided limits. So two-sided limits are basically, well, the way we write them is like this. We don't use a plus or a minus now. And these are just what we called limits. So if you just hear the word limit by itself, it means two-sided limit. Okay, so, and this is what we kind of did the first time. So let's do this in general. So this number here can be any number C. So it's what the value of f of x in some sense should be. But it has to be the same from both the left and the right. The left and the right. Left and right. Okay. And so in our previous example, so one key thing to know about two-sided limits is, limits don't always have answers. Sometimes they're undefined. And the two-sided limit is undefined if the two one-sideds don't match. So what we say is that the two-sided limit exists only if the limit from the left is equal to the limit from the right. So they have to match. It has to match whether you come from the left or the right. Okay, and then if they match, then this limit is whatever that number is, right? So in this previous example, so if we go back up here, if I asked what the two-sided limit of this one was, so that would just, I wouldn't put a plus or a minus anymore. This would, we would say does not exist, because these two numbers are different. 0 is not the same as 2. Okay, and that's because our picture was kind of strange, right? Our picture had this thing where, you know, from the left it was one thing and from the right it was another thing, right? And that meant there wasn't one single candidate to try to fill in what f of 0 should be. Okay, so that's two-sided limits. And, you know, like in this first example, we would have said the limit as x approaches 2 was just this number 4 because it approached the same thing from both sides. It approached this number 4. Okay. Okay, so that's two-sided limits. And then the final bit is there's one other thing we can use limits for. And that is for, let's zoom in a little bit so it's easier to write. Is for infinite limits. Okay. So in these previous things, when we approached from the left or the right or both sides, you know, the function kind of stayed nice and it approached certain numbers. But sometimes it doesn't. Okay. So let's say I had a graph that looked like this. So say it had a vertical asymptote. At, say, the number 3. And then it does something else over here. Well, let's make it even a little bit different. Okay, so say I had a function like this. And let's say this is -4. Okay, so when you have this sort of situation, and I ask, what's the limit as x approaches 3 from, say, the left? Okay, well, on the graph, as I approach 3, let's use a different color. As I approach 3 from the left here, the outputs are following this line, right? They're going way up here. So the outputs are getting bigger and bigger and bigger, and they really don't ever stop getting bigger, right? There's not like one particular number I can say like, oh, the function's heading to this number, right? No, it's like, if I just go a little bit further, it gets, you know, even farther. This thing is, whoops, this thing is just keeps going up forever, right? So in that case, if the function has a vertical asymptote there, we say that it goes off to infinity. And in this case, it would be plus infinity. If it had gone down, it would have been minus infinity. Okay. And so in this picture, if you took the one from the right, well, the right one's not too bad because as you approach from the right, you just follow it into this nice, good number 4, right? So this one would be just 4. And because these things are different, the two-sided one, we would say does not exist. And we'll often shorthand that by D and E. Okay. Okay, so that's sort of how infinite works. So one thing that you might be curious about is, there might be another situation where you have a function where they both go up. So say this is the number 5, and this is your f of x. Then here the two-sided limit is x goes to 5. Because from the left and the right, they both go up to positive infinity, the two-sided would also be positive infinity. So they have to match, right? If one's plus and one's minus, then it doesn't exist. Okay. So that's one thing about limits at infinity is, you kind of have to check the left and the right. Often for two-sided ones, you don't have to, but for infinite ones, you do.
Wait, I'm sorry. Could you explain the does not exist idea again? If it approaches from, I'm still kind of confused about that.
In this part here?
No, yeah, right there.
So the main idea so this was a two-sided limit, right? There wasn't a plus or a minus. So the main thing about two-sided limits is, in order for it to exist, the left and right things have to be the same thing.
Mm-hmm.
Okay, and what we saw here is from the left it was plus infinity, and from the right it was 4.
Oh, I understand. Okay.
So those are not the same thing, so it just can't exist. Okay. Yeah, and this really should say if and only if. So it's either way, right? If you have the two one-sideds are the same, then that's the same as the two-sided, and if they're different, then it doesn't exist. But no, that's a good question. And let me show you one last thing, and then I'm going to have you try some problems on the summary sheet. Yeah, let's look at this one. Okay, so sometimes you're not given a graph, and we'll talk more about how to do this next time. But let's try to compute the limit as x goes to 2 of x squared minus 9 over x minus 2. Okay. So what we'll learn a lot in the next couple sections is, whenever you're given a limit and you're trying to figure it out what it is, the first thing you should do is you should just always plug the number in. So if I plug 2 in for x, we might think, is that equal to 4 minus 9 over 0? So that's what minus 5 over 0. So that's undefined, right? Whenever you have a 0 in the denominator, dividing by 0 is undefined. But it gives us a crucial piece of information, because what it's saying is that as x gets close to 2, what's happening to this denominator here? If x is really close to 2, like 2.001, then this will be really small. This is getting really small. And so but the top is approaching minus 5. So if I'm dividing a number by a really small number, that makes it a really big number, right? Like if I take 1 divided by 1 over a billion, or something with a bunch of zeros, right? That'll just be like a billion. Right? So the idea here is, whenever you end up with a case where you have a number that's not 0 on top divided by 0. This means there's a vertical asymptote here. A vertical asymptote at x equals 2. Okay, so it's going to have some picture that might be similar to either this or like this. And we have to decide kind of how it looks. So that's the first thing, is to recognize that this is going to be an infinite limit because there's a vertical asymptote. Okay, so it's a good thing to keep in mind that vertical asymptote and having a limit equal to plus or minus infinity are kind of the same thing. Actually, that's the definition of vertical asymptote, is that the limit's infinity or minus infinity. Okay, so now how do we determine that? Well, the way I like to think about it is I would factor the top. You actually don't have to do this here, but in general, I think it makes it easier. Whoops. X minus 3. And I say, so this isn't technically correct, so I'm going to put this equality in quotes, but what I'm going to do is whenever I know something's an infinite limit, I'm going to do it from the right and the left. Because there's no way to just do the two-sided directly. You have to check the left and the right individually. So I'm going to do like from the right. And so what I'm going to do is I'm going to imagine, so like in these pictures here, what I'm imagining is, like if I chose a picture, a point that's really close to 3, but just a tiny bit smaller, then if the function's going up, that should be a large positive number, right? And if it's going down, it should be a large negative number. So what we're doing is we're just going to check the sign. Because I know it's going to be plus or minus infinity. I just have to figure out, is it the positive one or the negative one? Because I already knew from here that it's a vertical asymptote. And the idea is that I like to use is I just imagine like this. So 2 plus is not like a real thing. It's just, I'm just trying to imagine a number that's super close to 2, but just a little bit bigger. Close to 2, but slightly larger. That's what 2 plus means. And then I try to figure out, does this come out to be a positive number or a negative number? So I'm substituting a number that's close to 2 but slightly larger in. And then what you'll realize is, so this first thing, will that be a positive number or a negative number? So something a little bit larger than 2 plus 3 will be a positive number. Okay, something a little bit larger than 2 but really close to 2 will still be like close to 2. So if I subtract off 3, that'll be less than 0. So it'll be negative here. And then the bottom, if I take something slightly bigger than 2 minus 2, that's like, 2.0001, that's going to be a positive number. So the bottom's positive. So this is like plus times minus over plus. And overall, that becomes a negative, right? If I take a positive number times a negative number divided by a positive number, it'll be negative. And so the answer here is just negative infinity. Does that sort of make sense? And then you can do the same thing from the left. By plugging in a number that's slightly less than 2. So you would do it similar. You just plug 2 minus in. Something that's close to 2 but slightly less now, or slightly smaller. Okay. And so this one here will still be positive because it's like 1.99 plus 3, right? 1.999 minus 3 would be a negative number. But now on the bottom, I'm taking like 1.999 minus 2. That'll be a negative number now, right? So here I would get plus times negative over negative, which overall becomes a positive. Okay, so we figured out the left and the right limits. Were they the same? No, they had different signs. So this means that the answer is that it does not, the two-sided doesn't exist. And but what you can say is you can say that the graph had to look something like this. You know, at 2, there's a vertical asymptote, and from the left, it was plus infinity, so it had to blow up to infinity there. And from the right, it went to minus infinity, so you know, we don't know what the rest of the function looks like, but near the asymptote, we know it looks something like this. Okay. All right, so questions? I know it's kind of a lot to digest. Okay, so what I'd like you to do now is open up, I forget which number it is. If you go to today's checklist, it's the worksheet there. So if you go to Friday's checklist, and there should be a worksheet here. I'm going to put you into groups, and I'd like you to work through basically just start at the beginning and work your way down. So start with number 1, then try number 2, then number 3. Okay, does that sound good? And then me and you, will come through and help you if you get stuck.